On this computer. Here we go. Okay, great. Okay, so as I mentioned before, I have broken this this chapter into 2 lectures because I figured that, there's kind of a natural split. So the main source, as you guys know, is chapter 2 of the book Statistical Signal Processing for Neuroscience and Neurotechnology. The chapter was actually written by the editor, Ois, as well as another author. And today we're just going to be covering the first half of the chapter. So neurons are known to produce stereotyped transient spikes, right? So transient spikes are basically signals that appear and then they disappear, right? They go to zero or near zero after a certain point. And so neuroscientists oftentimes like to represent neural spikes as point processes. And the reason for that is because it's considered, it's widely considered to be the case that the timing of neural spikes is more or less the most important thing about neural activity. So of course, the spike shape, there are papers showing that spike shape influences things, sometimes learning processes and so on. But as a general rule, this is the piece of information that's of interest. And also, using individual waveforms, as was mentioned in the earlier discussion, oftentimes would produce files that are just way too big at this point. And so people like to use these kind of sparse point-like representations. And the premise of the spike detection and sorting that's detailed in this chapter is essentially that the timing of neurons is regarded as sufficient for decoding brain activity. So as I said, there's a caveat here that may or may not be true, but that is what we're assuming for the case of the chapter. So unfortunately, in vivo, things actually are pretty messy. Raw intracortical electrodes data produce non-stationary time series with transient spikes embedded into noise, which may or may not be weakly stationary. So what does that mean? So basically, we have a situation here where, you see these kind of long periods in the data where the average has shifted up or down, across some, median level, right? And so stationarity is essentially the assumption that, let's say you have a covariance matrix. So let's say you have a covariance matrix here that talks about the relationship between each of these individual data points, right? So normally, with a stationary process, we're talking about something that's very close to identically distributed and independent sampling, right? So in the case of IID, what you basically just have is sigma squared, right? Just all down the diagonal. And then everything over here is just 0 and 0. Okay, does that make sense? So that's something I'm sure most of you are familiar with. Now, there's a slight generalization of this, which is you can call something weakly stationary if the mean is still independent of time, and if the covariance is still independent of time. And there's a special way that can happen, which is, imagine that there's some scalar value or some other value, gamma 1, right, like this. And then say over here, it's also gamma 1 here. And then, let me put that, kind of align that matrix there. And then maybe, there's a gamma 2 out here. And what this is basically the distance in time, right? So you're going to have some symmetric distribution that tends towards 0 at the edges here. So it's going to still be like 0 towards the edges. And that, can in theory produce some of this noise, right? However, it's actually been shown Okay, so anyway, so basically, this is kind of the situation that we're in here, where we're seeing that there's kind of a median about which things fluctuate, but it's generally kind of staying within a certain neighborhood. And we know, through biological constraints that in general, even though things oftentimes are non-stationary, they're going to remain weakly stationary, right? And the reason that this is kind of nice is because you can do a variety of filters that will basically decorrelate these. So it'll kind of bring these over here down closer to sort of a zero value, right? So it'll kind of help to what's called whitening the matrix. So it'll bring it closer to something where these are zeros. Does that make sense? So that's what we're doing here. So basically, when we impose filtering, we can basically render the noise truly stationary in this respect. And then you can start to begin to see that there are these spikes, right? There's points where there are these like obvious deviations, although sometimes there's a little bit of ambiguity even in that case. And so neural spike estimation is the method by which we aim to basically go from this raw data to something like this, and then actually to these point processes that are kind of represented like that, over time, if that makes sense to people. And so the emphasis in practice is usually on spike detection and spike sorting. So NDS can estimate timing, duration, and waveform. So the timing would be, this point of interest. The duration would be the support, right? So in reality, even though we're representing this like as a point-like thing, it might actually extend over time, right? There might be some support region, a small interval of time over which the spike actually occurred. And then the other thing is that inside of there might be a waveform, okay? Now, for the purposes of, again, this kind of analysis, the data are always discrete because they're collected by a computer. And so even though this is supposed to be, a continuous waveform, we're just representing it as a vector, right? So this could still just be considered a vector, even though we're kind of, in our heads, we're imagining that it's actually a shape of a spike, right? So those are the three things that in theory you could detect, but in general, we're going to be primarily focused on just, the timing and attributing the source, which may or may not actually involve reconstructing the shape, okay? So the plan for today is that we'll be focusing on spike detection, and next time we will look at spike sorting, and then we'll implement what we've learned with some real data, and then we'll decide whether to move on to another chapter. So the case of discrete spike detection. Spike detection can estimate, as I mentioned, up to 3 parameters. Generally, by convention, we start with the arrival parameter, right? There's a variety of ways you could represent timing, but we're going to use the arrival parameter as well as the spike support, right, L, which can also, we can infer the end time of the spike from that. And then a waveform or shape S, okay? And additionally, as I mentioned, let Y be the observation vector of an electrode. So even though we tend to think of this as kind of continuous data, right, it's being collected by a computer, so we're going to regard this as a discrete vector. And let N be an appropriate noise process, okay? So again, what does a noise process mean? Well, that's getting into, stationarity and independent processes. So in general, we're going to be looking at, okay, so in general, what we're going to be doing is we're going to be looking at 2 different kinds of noise. There is electronic instrumental noise, which is stationary, zero mean, and Gaussian and white noise. So what do these things mean? The first thing is that, stationary, as I mentioned, implies that there is an independence of covariance and of mean over time. And And if it's strictly stationary, it's we're not going to see the long distance dependencies that I mentioned as being possible before. That's something called weak stationarity or second order stationarity. But if all of the moments are stationary, then you're not necessarily going to see that. The other thing is it's going to be zero mean, and it's going to be a Gaussian process. And so what does that mean? So that basically means it's going to follow something like a normal distribution, right, in terms of the distribution deviating from the mean, okay? And white noise just means that the frequency distribution is even, right? So what that means is that, if you have a function of frequency here, and then you have, the intensity here, intensity I, the distribution is just going to be more or less flat across the entire spectrum, okay? So that's fairly easy to filter out, right? That's like not too difficult to deal with. But the other kind of noise is biological background noise. And this is known to be non-stationary or weakly stationary and to be colored, right? Now, colored is just a very simple distinction. Just like before, if you have a frequency and then you have an intensity, what you might see is some kind of upward or downward sloping trend, right? So it's going to be kind of unevenly distributed across the intensity spectrum. Across the frequency spectrum, the intensity is going to be unevenly distributed. And, the reason that I mentioned weak stationarity before is because in the case of biological noise, we know that biological cycles affect intracortical background noise. And so we know that this is probably not true, but we're going to be assuming for the sake of argument, so that we can do the math, that it's Gaussian and weakly stationary, right? So again, just to reemphasize this, because I know these concepts may or may not be familiar to people, weak stationarity actually allows for some covariance between data. So you're going to sometimes see this kind of intervals where things are shifting up or down, right? But it's always going to sort of stay about a mean. Whereas we know in reality, it may be non-stationary. So like over the course of a 1 hour recording session, we may actually see some kind of secular trend, right? But we're going to ignore that for the sake of this analysis. Now, the classical approach to spike detection involves a simple hypothesis test. So basically, H naught just says that Y, right, the observation vector, is just equal to the noise process. So essentially the sum or a mixture of these two kinds of noise processes. So we're expecting it to just kind of look like this, right? You might see a little bit of that covariance that we can filter out using various kinds of filters. But in general, it's just going to be kind of like that. And then H1 is going to be one of those intervals, right, where you see a big spike, kind of like that, right? So it would be just like this interval here, where the spike began and ended, okay? And so those are the two hypotheses that we're going to be testing. Now, the way that we do this, for those of you who know statistics, this will be very familiar. We're using log likelihood ratios in order to test the hypothesis. So we have this test statistic T of Y, which is proportional to the log of the probability of Y given H1, right? So given the alternative hypothesis that we're seeing a spike, over the probability of Y given the null hypothesis that we're just in a noise region, okay? And gamma is just going to be the probability of the null hypothesis times the false positive cost over the probability of H1 times the false positive cost of falsely detecting a spike, right? So the reason that we have this FPC here is so that we can fix the power of the test. And we'll see later, we don't really use this quantity. There's another way of doing it. But this definition allows for us to kind of adjust the value of gamma as desired. And so when all the parameters are known, we can kind of do the Bayesian thing and look at the optimal estimator. So the optimal estimator uses the following decision rule. Basically, we're just saying that the test statistic is less than gamma, implies that we're in the null statistic region, or in the noise region. And when the test statistic is greater than gamma, then we're in the alternative hypothesis, we're in a spike region, okay? And there are two situations in this paradigm. When the spike waveform S is known, then it kind of simplifies the analysis. And then when the spike shape is not known, then there's a different way of doing the analysis that's a little bit less optimal. Okay. So when S is known, in the simple case, basically what we do is, we compute this log by, supposing, as I mentioned, that the noise is distributed normally, right? And so we're going to have this normal distribution here. It's a multivariate normal distribution. And what we're going to do is we're going to suppose that, we get this, this kind of covariance right here. And then for the alternative hypothesis, what we're supposing is essentially that we have the difference between Y and S, right? So that's the distribution that we're looking for here. And basically, if you just divide through, if you do the math, what you find is that you get this whole term here as being equivalent to the log likelihood ratio. And, I give an explanation. I'm not sure if people are really interested in kind of going through that calculation. Do people want to see that in detail, or should we just keep moving?
Yeah, I would like to actually go through.
Okay.
As a computer.
It's fairly straightforward. But let me just let me do that. Okay, so basically, right, we have this this distribution, right, and we're dividing one by the other in order to obtain this statistic. So let me think about this for a second. So let me get into.
Quick question is, in this example here, the uppercase sigma, is that just a variable or is that representing summation?
Yeah, so this is a standard convention in statistics. So sigma is kind of equivalent to the variance. Like if you've ever seen a normal distribution, but the difference is that this is a covariance matrix, right? And the reason that we're using the inverse here, we'll kind of discuss this a little bit later, but the reason is because it kind of undoes some of the covariance that confounds the test, right? So we're interested in a whitened version of the distribution. So the one that we're looking at looks kind of like this, right? It's got these spikes in there, and we're trying to distinguish the spikes from the noise, but the noise itself is weakly stationary, right? So, what does that mean? Well, that means that the covariance matrix sigma, right, it's obviously got this diagonal, but it's also got like a bunch of random terms in here, right? It's going to have some covariance terms that are non-zero out here. I want to use a different, I'll just call this lambda. That's not really a standard convention, but I want to distinguish it from the gamma values that we were talking about before. So there could be some random, gamma ij value or lambda ij values over here. Does that make sense? So this is like kind of, actually, okay, you know what? You don't really need the stationarity assumption. But I guess if we're going to stick with the strict stationarity assumption, then yeah, you can just do gamma 1, gamma 2, etc. Gamma 1. And then, right, so what we're trying to do by taking the inverse of this matrix is we're decorrelating everything, right? So the inverse of this matrix, taken on Y, right, which is the vector that has this covariance matrix, what it does is it gives us something that is essentially going to look like this, right? Right? It's going to be not exactly this, right? But it's going to be kind of as close as you can get to that. So in practice, if you were to actually compute the covariance, like the estimator S, right? If you had S inverse, this wouldn't be exactly equivalent to that, but what we're doing is basically we're getting as close as possible to this here as we want to be able to. And similarly for this one, right, what we're doing here is we're saying, okay, well, suppose we're in the region with the spike and we know what the spike looks like. Well, all we have to do is subtract the spike and then whiten it using the inverse of the covariance matrix. And again, we get essentially a very nice unit normal distribution, right? Does that make sense? So that's the intuition behind why we're doing this. And, if you want to do the calculation where we do the ratio, essentially, right, we have this 1 over, 1 over 2. Hang on, let me just take a look at the, right, yeah, it's absolute value. Is that outside or inside? It's outside. Oh, you know what? There's a typo here. This should be square roots.
Oh.
Sorry about that. Right. Okay. And this should be in there. Yeah. So what we're doing, here we're taking the absolute value of the determinant, right? That's what that is. And it doesn't really matter for the purposes of dividing through, right? Because we have this e to some value here, right? And that's going to be essentially, right, the ratio is H1, so this one, on top of this one. So we're going to have, negative 1/2 y minus s transpose inverse, and then we're going to have y minus s. Okay, and then we're going to divide through and take the log, right? And then we're going to have this same term. And then we're going to have e to the, in this case, negative 1/2. And then it's just going to be y like that, okay? And so, what do we do with exponents, right? So these cancel out. What do we do with exponents, right? When we divide through by an exponent, we just subtract. And so we end up getting, right, log e to the, or let's do the exponent notation. It's a little easier to read here. So now what we have is, okay, negative 1/2. And then we're subtracting another negative 1/2, right? So if we want to just factor that out, then what we get is essentially this y minus s transpose inverse y minus s term minus, right, because we factored out the negative 1/2, y inverse y, right? And it's fairly easy to see, like something, I'm not sure how many of you are versed in matrix math, but basically it's distributive, right? So while you can't, it's not commutative, you can distribute all of these out, right? And when you do that, right, what you end up with is essentially, okay, so the other thing is we're taking log and x, so this can go, it cancels out, right? So now we have negative 1/2, and let's just, we'll go through the calculation for clarity. So we can distribute the transposes here. So let's do that here just so that we don't have to rewrite the whole thing. So we have these transposes distributed, and then we can distribute the multiplication. So we get y transpose y minus s minus s transpose y minus s minus y, y, okay. And, that ends up being equal to, let's see how we do this, okay. So now we distribute to the right, so we have y transpose versus y, right? And that cancels out with this one. Does that make sense? And then we have, this minus y transpose s, s, and then we have, here we have minus st inverse y plus st inverse s, okay? And, something that we should note in order to kind of get to the result that I showed up there is essentially that sigma inverse, right, sigma is a positive definite matrix, right? So it's symmetric about the diagonal. And so what that means is that, if you take the transpose and then the inverse, that's equal to the inverse transpose, which is just equal to sigma inverse, okay? So basically, transposing it doesn't do anything, right? And so because of that, we can just take the transpose. And then the other thing to note is that these are vectors, right? So all you're doing when you transpose a vector, right, y to yt is just equivalent to taking a column vector and just transposing it into a row vector, right? So that also shouldn't make any real difference in terms of matrix multiplication in this context, right? So since it's essentially like actually, hang on. Let me see something real quick. I think I may have when I was rushing here. It's going to be S transpose Y transpose over here. YS. Oh right, yeah. Okay, okay. So all like if we take the transpose, we can just switch these terms, right? So if we take the transpose of this here, or actually rather. Which one did they choose conventionally? Yeah, they chose this one. Taking the transpose of this, essentially, if you're going to flip this into a column vector, right, then it needs to be right composed for it to look the same. And if you're going to flip this into a row vector, then it needs to be left composed, right? And so this here is equivalent, right? So you can basically just say that yt inverse s, right, is equal to its transpose, equals the transpose, right, which is just equal to this guy here, st inverse y, right? And so as a consequence, we just basically what we've done is we've canceled this term here, and we're rolling these two terms into just 2, right? So this is now, I wish I had a little more room here. I guess I'll just create another page, but that might be confusing for people because then we'll lose track of where we are. And we just kind of, just gonna move this up. Is that okay for everybody? So basically what we're doing is we're just rolling these two terms. So we get -1/2, and then we get, times -2 st sigma inverse y, and then we get this kind of, guy over here plus st sigma inverse s, okay? and then we distribute out the half, and we get this this formula right here. Okay. Now, in practice, since gamma is not really being fixed, we're not directly concerned with the exact equality, right? So we can set the test statistic, right, of y to be just, the part that depends on y, because S is known, so it's not going to change. And so for the purposes of doing a test statistic, it doesn't really matter. And so that's what we do in practice is, and this is very common, like oftentimes in statistics, you'll find that there'll be either coefficients or extra constant terms that just get knocked off in order to make a test statistic easier to compute without really, impacting the utility of the statistic. So in practice, we just use this test statistic, S transpose sigma inverse of y, which is, if it's less than gamma, then we get the null hypothesis, and if it's greater than gamma, then we get the alternative hypothesis, right? And as I mentioned, right, the inverse covariance matrix decorrelates the variables and acts as a whitening filter, right? So this is one way to obtain stationary noise that, just as was shown in the figure that, took us from the filtered to the unfiltered data, right? So that's kind of like, again, just kind of to really drive this home because it's very important, right? We start out with data that's like this, and the spikes might not even be clear, but then what we do is we transform it into this, strictly stationary, usually Gaussian distribution where the spikes stand out a great deal, and oftentimes it even enhances their sort of fidelity there.
So is the purpose basically to kind of determine, as we look at the data set, to determine whether the probability that we're just looking at a bunch of like stochastic data versus the probability that we're looking at data that actually has a pattern?
That's exactly right. Yeah. So the point in this case is that we're making this very simplifying assumption at the outset that our goal is to take this time series, this one here, and after we do this, the next step, right, in this process is essentially we want to then turn this, right, into a sequence of spikes, right? So we just want to extract those two spikes, represented as a sparse process. Does that make sense? So it ends up looking like a vector of ones and zeros, right? So you're gonna have like 0, 0, 1, 0, 0, 1, 0, 0, 0. Does that make sense? So that's what we're doing here is we're saying essentially, you can even directly map the null hypothesis and the alternative hypothesis to this. We're basically saying that for a sequence of intervals, is it the null hypothesis? If so, coded as 0. If it's the alternative hypothesis, coded as 1, right? So that's what we're doing. We're essentially using a statistical test like this to decide at a given interval, right, at a given time scale, whether we're in a region of noise or whether we're in a spike region, a region of noise, spike region, and so on, right? And we go through and we do this, and we create this simplified spike train representation. Now, again, we are throwing away some data that could be useful, but that is the point of this spike extraction. So now, when S is known, actually, you know what? I think I did this a little impromptu. I was preparing it just kind of yesterday. So some of the titles and things I didn't have a chance to review. But basically, this is actually just we're still looking at when S is unknown, right? So we're looking at the tail. So basically, this is setting gamma, right? Setting gamma. So as I mentioned, we tend to pick gamma based on the power of the test, right? And based on the relative cost that we're interested in. And so basically, suppose we want a test that catches 80% or probably more, right? We'd probably want a fairly sensitive test. So suppose we want a test that catches like, 90% of the spikes, and then false negative rate is also fairly low. What we're going to do is we're going to use this kind of standardized tail distribution, right? So what we have is we have this unit normal distribution, and we have this test statistic that we've been using, right? And we say, okay, gamma minus the test statistic over this scaling factor, right, which is √2 times ST sigma inverse S, right? Now, this, right, the reason we're scaling this this way is because under the, in this situation, we know the variance of the the spike, right? This is essentially the whitened variance of the spike, right? So it's the thing that's kind of valid to compare this to. And we're trying to say, okay, well, is there a difference, right? Is there a significant difference between the test statistic here and gamma, right? Because remember, if we are in the alternative hypothesis, this here, right, is greater than gamma. And so what we're going to be seeing here is essentially that this is going to be a negative value, and it's going to be, sizable if it's significantly greater than gamma, right? And then what you're going to do is you're going to say, okay, well, right, and then also why are we subtracting this way? Because you'd think you'd want a positive value, but the reason is because we're looking at this part of the tail. It just simplifies the calculation. In theory, you could look at this part of the tail as well, but it's not as, right? So what we're doing is we're basically saying, okay, suppose we have a gamma here, right? It's all the way up here, right? And we're saying, okay, well, gamma minus this test statistic is going to encompass this region here, right? And then what we're interested in is 1 minus that, so we get the complement, right? Which is this region here. We're asking essentially if the test statistic is in this region, right? This is very similar to z-tests or t-tests, if any of you are familiar with that sort of thing. And then in this case, all we're doing is we're just basically saying, well, for the null hypothesis, since gamma is supposed to be greater than t under the null hypothesis assumption, which assumes that, that this is not, that this is equal to, hang on, actually, let me, yeah, I mean, so they actually really didn't get into detail in this, and I didn't have time to really delve too deeply into why this distribution is the way that it is. But this is sort of the gamma value, right? So this is the alpha value for people who know about this. This is the beta value, right? And so basically what we're doing is we're saying, we have the probability of the true positive and the probability of the false negative here. And one nice thing to note about this is that the probability of the true positive is just equivalent to the ratio of the true positive over the total positives, right? It's normalized. And so that is, in fact, the power of the test. This is equal to the power of the test. So if you wanted to select a gamma with a specific power, then you just pick a gamma that gives you a desired power, right? You fix everything, right? Because you have this test statistic here. You've already done that. And you just, select a gamma that's going to give you the desired power on this distribution, right? Does that make sense? Now, the reason that you would also be interested in computing the probability of false negative is because while it may be useful to be thinking only about the power of the statistic, oftentimes what you're really looking for is a trade-off between false and positive and false negative rates. And so what you're going to do is you're going to try to find like some point on the envelope that would be desirable for your particular case. And you can compute this, for any given data set, right, in order to get some kind of optimal value that you might be interested in. So, you wouldn't do this if you were doing online learning, but suppose you had a training set and then you wanted to extrapolate to a test set, right? Like maybe you take a half hour of data from someone and then you run this analysis in order to set the gamma value. And then that's the gamma value that you use for your test when you're doing the actual experiment, right? So that's an example of how you might use that. Now, when S is unknown, we simply do the Bayesian thing and we maximize the value of this probability distribution that we have here, but assuming that S is a variable, right? We say, okay, what would the maximum value be? Well, again, for those of you who are familiar with normal or Gaussian distributions, right, it's centered about 0, right? And that is the highest value, right? So all we have to do in order to get that is we just set S equal to Y, right? And that maximizes this probability of Y given the alternative hypothesis and given S, but when we treat S as a variable, what's the safest assumption? Well, clearly the safest assumption is just something in this region here, right, at the peak. And so that's what we do. And we end up getting a very similar test statistic. In this case, we just, we set S to Y. And it turns out to be chi-squared distributed. And the analysis is fairly similar. So instead of using a t-test-like situation here, what we would use is an f-test-like situation. And so that's something that's fairly straightforward. And I figured you guys might be a little tired of going through detailed math at this point. So I kind of glossed over that. Now, what are some caveats? So while understanding the classical approach is important, in practice, scientists don't actually use the statistically optimal test, right? And there's a couple of reasons for this. One of them is that it's actually not optimal, right? As we discussed from the outset, the assumption that we made isn't necessarily true, right? So because the assumption of stationary noise is often violated, it's kind of like, suppose you have an argument, right? A statistical argument. One argument is purely mathematical. It's very solid at this point here, right? So you have this, math proof. And then you have these assumptions. And then you have a conclusion. Now, if these assumptions are sketchy, right, then of course the conclusion is going to be sketchy, even though this whole thing here is airtight. And so, if you use a more robust empirically based test or method, then the proof is sketchy, right? But you also don't have as many assumptions, right? So you have better assumptions, and then you don't really have a proof. You have more of a heuristic, and then a conclusion. And, more or less, you're going to get the same kind of sketchiness in a lot of situations. It might even be better, right? If you empirically test it, it might turn out to be better. That's kind of the attitude that data scientists take as well. For example, the use of neural networks, even though we don't really understand a lot about what they're doing, you're using heuristics in order to come to a conclusion, and then you're empirically validating it. And from the scientific perspective, in a set of weak assumptions, in conjunction with a mathematical airtight proof, is about as good as a set of better assumptions with a heuristic, right, in a lot of cases. And so that's one reason why, we don't necessarily use the optimal test, right? The other thing is that all of the normality assumptions require large sample sizes, right? So for this to even be reasonable, we need pretty big, trailing sample size. And the problem with that is that computing the statistics can be expensive, right? If you're trying to do real-time data analysis, right, or you're trying to compute spike times on a low-powered implant chips, then those costs end up really, interfering with your experimental work, right? So in practice, scientists, especially people working in brain-computer interfacing, right, where you have an implant that you're trying to use for some engineering purpose, they want to compute the spike times on the chip because oftentimes transmission is an issue, right? We don't really have great wireless transmission in these small chips yet. And you want to be able to detect spikes in real time. So even if you have the computing power, you don't really want to be like, waiting until you have like a large amount of data in order to be able to do this. And you want to be able to deal with the reality of non-stationary biological cycles, right? So as a consequence, it ends up being that you can actually use heuristics oftentimes, and they work out okay. And so, in practice, there's a few, practical methods for doing things that are a bit less rigorous, but work pretty well, and they're fairly robust. We're actually not going to discuss number 3 because it bypasses the spike detection step, which is the topic of today. But basically, there's voltage threshold methods, and then there's transform-based methods. Okay, so we'll get into what each of those are. In practice, it's often robust to use a fixed voltage threshold method to identify spikes. And so the simplest case is where you just make some really strong assumptions about what's going on, but you know that they're wrong, and you're just kind of using a heuristic, right? So it's kind of like with the statistical case, right, where you're making assumptions that you know are wrong, but then you kind of empirically go, well, did they work out okay in general? And so you pick out all of the points, Ti naught, right, where there's a fixed voltage threshold that's crossed, right? So you're going to set some voltage threshold, and you're just going to have this data, right, which may be up or down, etc., right? And you may do some transformation on the data, right? You may at least transform it into a stationary form, right? You're going to put some filter on it, and then you're going to say, okay, where does the voltage or the power cross once we've fixed this? And in practice, you can even do it with this case, right? It oftentimes still works out okay, although it's going to miss quite a few spikes in some cases. And then what you do is at this point where there's a crossing, you extract a spike vector, okay? And you say, okay, well, empirically, I know that oftentimes, if I go back 0.5 milliseconds, and then I go over here to plus, 1 millisecond, then I'm gonna capture like a pretty decent amount of these waveforms, okay? So it's often desirable, even though it's suboptimal, because it's very cheap, right? This is something that even a small chip implanted in the brain can actually do. Many spike waveforms deviate from the assumption that the support L is 1.5 milliseconds. Right? So that's actually, that's kind of a caveat of this one. And it turns out to be very important down the line, right? So if L is too large, then noise gets mixed in with the waveform. If L is too small, then important spike features can get discarded. And either issue can harm spike sorting downstream. And so this is something that people have tried to deal with. You can address this problem by recentering the vector about a maximum, right? So like, say you have a naive vector, a window, maybe it's even a little bigger, maybe you go back like, 1 millisecond and then you go forward like 1.5, okay? And then in here, there's some peak, right? So you just find the maximum and then you recenter the data, right? So that it's centered exactly about the peak. Okay, and that and then you might even shrink the size of the window or something. So, but it would be an assumption, a heuristic. It would just be a fixed algorithm that has no interest in any statistics, and that can work out okay. But it does bring back some of the expensive computations, because finding the maximum in a vector is requires you to basically run through a for loop. But there are people who have worked on some alternatives. I didn't really get into it here, but as far as I can tell, the 2 papers that he cited are actually the only 2 papers that still exist, at least on Google Scholar, on this topic. And so my thinking is that maybe computers have gotten a little bit more advanced since 2010, and maybe this issue is no longer such a problem. Maybe it's reasonable to expect an on-chip device or an in vivo device to be able to actually do the recentering. I'm not totally sure about that yet. So in addition to fixing L, The voltage threshold method assumes that the spike signals and noise are uncorrelated, right? So again, it's making some pretty strong assumptions, and that the noise is white and Gaussian, right? So, basically, I think I misspoke a little bit before when I talked about this kind of heuristic versus proof thing. But the idea is that if you start with wrong assumptions, right? If you start with wrong assumptions, and you want something that's going to be approximately true, in this case, right, if you're starting with wrong assumptions, then a heuristic is about as good as a proof, right? And that's, in practice, oftentimes ends up being the case, right? You might get slightly better performance with the proof, but, more or less, a heuristic can oftentimes be as good. Now, there are some additional caveats, and these are kind of important ones. Spike signals and noise are often correlated because noise can capture the context of a neuron's extended dendritic network, right? So basically, one of the more recent findings about neurons, or actually this isn't that recent, is that basically, there's going to be a region where inputs from other neurons are going to basically cause a spike. But then there's going to be this kind of outer region, where an input into this region won't necessarily cause a spike, right? There won't necessarily be a spike into this region, but it will prime the neuron. It'll make it more sensitive, or it might even change its learning disposition, right? And so this noise oftentimes actually captures this more distant region. It captures some of this activity. And so noise can be important, right? And that's actually an important caveat for the heuristic methods, as well as, all of the statistical methods that try to just completely disregard the noise. And so there's, and then the other thing is that it could capture the activity of large distant neurons. So, right, you might have like a big neuron over here, with its own long projections, and maybe one of them, goes into here, and maybe it even gets all the way into there. And so if you're hearing the activity of one of these big distant neurons here, that could conceivably actually trigger a spike if it's like a really influential neuron. And so that's another reason why it might be relevant. Although in theory, if you had all of the spike trains of all the neurons, then this would become less important. Okay, so then the second method is transform-based methods. So basically, oftentimes these time domain models, right, like where you use a heuristic especially, they tend to underperform models in various transform domains. Early work focused on the frequency domain transformations, such as a local Fourier transform. But one of the problems with this is that, again, you have to do spike extraction based on a heuristic, right? So imagine you're using a time domain thing to do spike detection. You extract this region, and then you analyze it as a local Fourier transform in some frequency domain where it's easier to identify. That's going to improve performance by a bit, but the problem is that if you're cutting up the spike vector incorrectly to begin with, then it's going to have a deleterious effect on the performance of this kind of thing. And so what ended up happening is that people then turned to wavelet techniques, which capture the transient nature of neurons, right? So the difference between Fourier transforms, which basically breaks something down, let's say you have a time series that's like, this, and it's going to break it down, starting and ending strictly at the points that you specify into these, higher frequency. These are supposed to be regular, by the way. They're not drawn correctly, but, and then you're going to be these lower frequency regular rhythms, these even lower frequency regular rhythms, and so on, right? So you're going to break it down into these various frequencies, but it's going to be this kind of discrete thing. A wavelet, by contrast, basically convolutes this kind of breakdown with a normal distribution. So what you get is you don't have to have a strict cutoff. You can just have something that kind of, creates a profile, kind of looks like this, right? So it's kind of convoluted with a normal distribution. You can just kind of see that it reflects the fact that a spike is going to look like that up close, right? And so that actually allows you to kind of circumvent the issue of imposing arbitrary cutoffs. And in fact, this method ends up being useful for spike sorting, and it can kind of, you can use it for spike detection strictly, or you can use it for spike sorting. The only thing that I'm going to talk about that today is I'm just going to mention that it tends to, strongly outperform time domain models in the context of S being unknown, right? So here we have this estimator, right? And then here we have this estimator, I think it's, we have this estimator here, right? And here you can see the difference is not really that significant, although you do get modest performance gains. So it's worth it to do if you can afford the computation in both cases. But there is like just an unbelievable gap when we don't know, when we make the Bayesian assumption here, and then just try to do a time domain analysis versus transforming into the wavelet domain and doing a test there, okay? So that's just an important result, and that's what I want to leave you with today. We'll actually start with the mathematical foundations of wavelet transform methods as an entryway into spike sorting next time. And so I figured that would be a good time to stop, and I think I was right. It took about an hour to get through the material here. Does anybody have any questions? No questions? Would people have preferred maybe a less technical presentation next time, or wondering what's going on with people?
I think.
Go ahead, please.
I was going to say, I think the technical details are definitely helpful to an extent, because definitely if we're going to apply this at some point, we'll need to we'll need to implement, be able to implement some of these mathematical functions in code.
Right. Yeah, and you don't. I mean, like the spike detection stuff. This statistics, like the test statistic, you don't need to like understand it at like a super deep level. I just want you guys to be aware of the math, because it is very similar to lots of other test statistics. It's just kind of a special case of all the other test statistics that people do. And I wanted you to kind of see that it's just a simple hypothesis test.
I feel like it's good to know that these wavelet methods are so powerful for this purpose.
Yes, yeah, they can be very powerful. And so they're by far the most preferred transform-based method. Did anyone have any questions? I know a few people were able to jump in with questions, but I didn't really stop for questions, and I'm wondering if people had any points of clarification that they wanted.
Can you go over like the technical details of performing a transform-based threshold spike detection?
Yeah, could you repeat that? I think you've got a little bit of static.
Okay. Could you go over like the technical details for performing a transform-based threshold spike detection?
Right. Yeah. So that's what we're going to do next time. We're going to start with that next time. I do have some notes on it, but I think it would be a bit impromptu if I did that right now.
And could you like go over some of like how to perform a ROC?
How to perform
a receiver operator curve?
Oh yeah, that's very simple. Okay. In fact, this here is a receiver operator curve. That's what we're using to compare these methods.
Yeah.
right?
Yeah.
So in the case of the time domain, what you would be doing is you would just be, these look like theoretical computations, right? So what you'd actually be doing is you'd just be looking at this math up here. Right, so you'd be looking at how to compute the false positive rate and the false negative rate. So, you know, let's see if we can, so let's go down.
Yeah, can we actually just look at the curve and explain how the graph is generated?
At the code.
Oh no, the curve.
Right. Yeah. So basically, what we're seeing here is essentially this is the true positive rate, and this is the false positive rate.
Can you guys hear me?
Yeah. We can hear you.
Okay.
And what we're doing is we're essentially we're varying along gamma, right? So which gamma do we want to set, right? Like if we want to increase gamma. And so that's the hidden parameter. I think that's why it might be a little bit confusing to understand this. So there is kind of a third dimension here upon which both of these depend, right? Like you could have a graph of, you know, where gamma is the covariate, and then you have like TP, right? And then here, you know, you might have one that's like gamma, and then the probability of FP, right? And, you know, each of these are going to go up. So like, for example, if you are trying to detect more true positives, you're going to increase the value of gamma here, right? And you know, that's going to decrease this value here, right? It's going to make this region over here smaller in this setup, okay? But increasing the value of gamma here, right, instead is going to push things down, right, along this, you know, respective curve, along the beta curve. Can you see how that works? How if you increase gamma here, it increases the difference between these two, or decreases the difference between these two because we're assuming that this is greater than this. Whereas here, it's increasing, you know, the position, right? And so what happens is basically that as you increase or as you decrease the value of gamma, right? So as you decrease the value of gamma, you're going to see, on the one hand, obviously the true positive rate at some point is going to 100, and then it's going to like start to dip down, okay? And then similarly, you know, you're going to start to see a lot of false positives as you decrease the value of gamma because you're being less rigorous, right? And the relationship between these two functions gives you the receiver operator curve, right? Does that make sense? And so then what you're doing is you say, okay, well, you know, for a given value of gamma, you know, say over here, this point, what is the true positive rate, right? Let's say it's, you know, we pick a value for gamma here, and this is the false positive rate, and then we pick a value for gamma here, and this is the, you know, true positive rate here. That each of those represents just like a single point here, okay? It just represents like, you know, the trade-off between these two things. And the reason that there's a trade-off is because of the fact that, you know, as you make the test less rigorous, right, you're going to increase the number of false positives. And as you make the test more rigorous, you're going to decrease the number of false positives, but you're also going to decrease the number of true positives. You're going to get false negatives, right? Does that make sense?
Yeah.
So that's, yeah. And so that's actually what we're seeing. Did that clarify your question?
Yes, that does make a lot of sense, and it does it looks much easier if I have a closer look at the graph.
Yeah. It's fairly straightforward, but you're right that it's a little bit mysterious because these are both functions of gamma, right? So this is kind of like an implicit function, right? It's a two-dimensional implicit function of gamma. We're basically saying, we have some I guess let's call it R for rigor of TP FP and then of gamma, right? So that's kind of the form of this, but we don't really care too much about gamma because we're just worried about the trade-off, right? We're just worried about, okay, once I know which one I'm interested in, I'll pick a point and then I go back and I say, okay, which gamma was that? And that's how I pick a gamma value in practice, right? That's why this whole thing about a ratio for the rigorous statistical tests doesn't matter too much, because in practice we're imposing a cost that forces gamma to give us whatever point on the ROC curve or whatever power we want.
Yeah, looking at that curve, it seems like it almost makes sense to find an inflection point. In other words, like if you see where the slope is like very, very, like if you look at the transform domain, you look and you see the slope is very, very steep at one point, but then there's a very real kind of like inflection region where it becomes less steep, and it seems like it makes sense to find a point that's like right about there, so that you end up like maximizing the true positive rate while still keeping the false positive rate, very low, like right around 0.1 or less.
That's definitely true, and I think that in a lot of cases that would be reasonable, although it would depend on the application. Like for example, suppose you're doing a pre-processing step, but then you plan to actually drop additional candidates later. Then in that case, maybe a high false positive rate would be acceptable. And so this little gain here, if you really want to make sure you have everything, because you're like being a scientist and you want to make sure you have like a super rigorous spike train to release to the public so that people can analyze it. In that case, you're going to want a really strong ground truth. So you might first run a filter that extracts vectors this way, and then run another test to figure out whether some of these are actually false positives to try to bring that rate back down, right? But in general, I think you're right that you would pick an optimal trade-off where you have fairly small numbers of false positives.
Okay.
So, as I mentioned before, I am looking for raw neural electrode data. So if anyone knows of a possible source for that, that would be real helpful, because, I don't want to just like go over the chapter, right? Most of you guys want to eventually, either you have an interest in this for independent reasons, or you actually want to do something with this knowledge. And so I'm assuming, or I'm catering to those of you who want to do something with the knowledge, and I want people to have the experience of writing up some code, maybe having a little something that you could write a blog article about, or do whatever you want to do with it. And so that's something. If anyone knows of a lab that might be able to provide a snippet, if the file's too big, just something short enough for us to do long enough for us to do an analysis, but short enough that it's not like a big hassle to transfer the file.
I might be able to get something. I can ask people from my PhD lab.
Okay, that'd be great. That'd be real helpful. And the other thing, this is a little bit of shameless self-promotion, but I'm just getting started in the neural, data science field. And so I don't know, I'm not assuming you thought positively of this presentation, but if you did, just go to LinkedIn at Oliver Shetler and, endorse that I actually know statistics, or that I actually know neuroscience. Because I just recently made my LinkedIn profile my academic one, and so I'm looking for those kinds of endorsements and things. Obviously, on the other hand, if you don't think I was competent, then feel free to just politely ignore that request. I'm going to stop recording now so that we can have a more free discussion.